From the earliest fireside stories to the soaring spectacles of modern cinema, humanity has been haunted by a single vision, the dream of leaving the ground behind and rising freely into the open air. The ancients told tales of winged gods who carried themselves across the sky with effortless grace. They spoke of fiery chariots that climbed from the earth into the realm of the stars, of enchanted carpets that drifted above deserts, of towers that could reach the heavens. All of these myths, spread across cultures and centuries, shared a common yearning, the desire to escape the unyielding pull that chained every creature to the soil. Gravity was never named in those stories, yet it was always the antagonist, the invisible warden of the human body and the human imagination. Consider the tragedy of Icarus, the boy who fastened wings of wax to his arms and dared to challenge the sky. His story is a warning, but it is also a confession of longing. It reveals that the Greeks, with their mastery of philosophy and geometry, could already conceive the idea of a person breaking free from the ground. In India, the Sanskrit epics describe the Vimana, divine chariots, that rose through the air like thunderclouds, carrying warriors and sages beyond the reach of ordinary men. In the Middle East, one finds tales of King Solomon controlling spirits that could raise him aloft. In the medieval world of Europe, witches were said to fly across the moonlit sky, saints were believed to levitate in moments of holy rapture, and angels descended with wings of light. Each of these myths reveals more about us than about nature. They are mirrors showing our dissatisfaction with being bound, our hunger to become lighter, freer, unshackled from the earth. The arrival of science did not end this hunger. It only changed the language of our dreams. When balloons first carried human beings into the sky, crowds gathered to watch as though witnessing magic. The Montgolfier brothers in the 18th century lit fires that filled great silk envelopes with hot air, and suddenly, the impossible was real. The human body could rise. Yet the method was fragile, dependent on weather, slow, and bound by fire. Soon after came gliders, then airplanes, and then rockets. With every leap in technology, the dream of true mastery over gravity seemed one step closer. But rockets revealed the cruel mathematics of gravity's grip. To climb even a few hundred kilometers from Earth required engines burning through thousands of liters of fuel every second. Every launch was a violent battle against the planet's pull, won only with brute force and staggering expense. The dream of easy defiance remained out of reach. Science fiction became the theater where gravity could finally be conquered without cost. Writers and filmmakers imagined sleek ships, hovering silently above alien landscapes, cities that floated among the clouds, machines that defied weight with a hum of unseen energy. In those imagined futures, gravity was not an obstacle, but a tool. A spacecraft could land gently without expelling fire. A soldier could step into the sky. A city could drift across continents. These stories did more than entertain. They kept alive the possibility that one day physics itself might yield a loophole, that gravity could be bent, cancelled, or tuned like sound from a string. Yet the sober fact remains. Gravity is not only a force, but also the stage upon which all other forces play their roles. It is the weakest of the known fundamental interactions, far weaker than electromagnetism. Yet because it acts on all mass and all energy, it shapes the large-scale architecture of the universe. Stars ignite because gravity compresses gas until fusion sparks within. Galaxies hold together because gravity weaves their stars into spirals. Black holes, the most extreme objects we know, are simply the result of gravity overwhelming every other force. Gravity is the sculptor of the cosmos, and that means it is also the greatest obstacle to any attempt to control it. To conquer gravity would not be like inventing flight or electricity. It would be to seize a tool that nature uses to design planets and stars themselves. Still, we are compelled to ask the question, if we can harness electricity, if we can split the atom, if we can manipulate quantum fields to build computers smaller than a fingernail, why should gravity be beyond us? The difficulty lies not only in its strength or weakness, but in its nature. Electromagnetism is easily controlled because it has positive and negative charges that can cancel or combine. Gravity, as far as we know, has only one kind of charge, mass and energy, and there is no negative mass with which to cancel it. To change gravity, one must move immense quantities of mass or bend space-time itself, which seems hopelessly out of reach. Yet every scientific revolution has begun with what seemed impossible. Imagine the perspective of a human being in the 19th century, before electricity filled cities with light. To them, the idea of carrying a device in a pocket that could transmit a voice across oceans in an instant would have been fantasy. Yet by the end of the 20th century, such devices were so common they seemed ordinary. The question is whether gravity will follow the same path. Is it a frontier that technology will one day breach, or is it a barrier woven so deeply into the structure of reality that it will always remain closed? Before we can answer, we must first understand. To ask if gravity can be manipulated, we must know what gravity, island, not in the language of myths, but in the language of physics. We must revisit the moment when Isaac Newton first wrote the law of universal gravitation, and when Albert Einstein transformed our understanding with general relativity. We must consider whether gravity is a force at all, or whether it is geometry, or even something emergent from deeper principles we have not yet fully grasped. Only then can we return to the question of control. And so, the journey of this book begins. From the firelit myths of ancient storytellers to the precision of modern physics, we will follow the trail of humanity's most stubborn dream, the wish to slip the bonds of gravity. We will trace how our ancestors imagined it, how our scientists described it, how our engineers wrestled with it, and how our future may yet transform it. To ask whether gravity can be bent to human will is to ask one of the most profound questions science can pose. But before we seek the power to change gravity, we must learn its true nature. That is where we turn next. The ancient imagination did not fail simply because it lacked technology. It failed because gravity is more relentless than almost any other obstacle nature has placed before us. When people looked at birds and thought perhaps wings alone could let them rise, they misunderstood the price that must be paid. A bird spends every moment of its life in a constant balancing act, burning food as fuel, converting muscle into motion, and shaping air into lift. To human eyes, this looks effortless, but to physics, it is a transaction, a debt repaid second by second. When people dreamed of levitation through prayer, through incantation, through mystical machines, they underestimated how deeply gravity is stitched into reality itself. It is not an enemy that can be ignored. It is the ground note of the entire cosmic symphony. Even when humanity succeeded in lifting itself skyward, the victory was partial and costly. The first balloons could ascend but not steer, drifting helplessly with every gust of wind. Airplanes solved the problem with engines and wings, but they remained tethered to Earth's atmosphere, dependent on air for lift and thrust. Rockets finally broke free of the air, but at the cost of colossal energy, roaring flames, and delicate balances of fuel and structure. Every astronaut who has seen Earth from orbit knows that their freedom came at the price of precise mathematics, thousands of hours of engineering, and a narrow window where everything must function perfectly. Gravity has never truly been defeated. It has only been negotiated with, outsmarted in temporary ways, sometimes resisted, but never cancelled. This stubbornness of gravity is part of what gives the dream its enduring allure. To imagine life without gravity is to imagine an entirely different kind of existence. Picture a child tossing a ball and never seeing it fall, or a builder stacking stones that float where they are placed. Imagine travel where vehicles rise gently into the sky, floating without fuel, carrying people across continents with no runways, no noise, no pollution. These visions are intoxicating because they are so unlike the world we know, a world where every motion eventually ends with a fall. When storytellers invent anti-gravity machines, they are not just predicting a new technology, they are sketching an alternate physics, a reordering of reality itself. In science fiction films and novels, the control of gravity is usually shown as simple, silent, and total. A pilot flicks a switch, and the ship hovers. A city floats above a gas giant, balanced against storms that rage below. Soldiers leap impossible distances because their armor bends the pull of the planet. These images are thrilling not because they are plausible, but because they speak to a deep wish. They suggest a world where human beings finally hold dominion over the very fabric that has always held them down. They suggest that civilization could escape not only its planet, but also the limitations of energy and matter. In such futures, transport is free, energy is limitless, and exploration has no bounds. Yet when physics speaks, it speaks with stricter terms. Gravity is not an optional feature of the universe. It is the mechanism by which stars form, planets orbit, and galaxies dance. Without gravity, the cosmos would be a mist of particles drifting apart forever, never gathering into suns or worlds or life. To manipulate gravity would not be like inventing a new tool. It would be like seizing the architect's pen and rewriting the plan of the universe itself. This is both exhilarating and sobering. It means that the prize is unimaginably great, but also that the barriers are unimaginably high. One reason gravity has resisted control is that it does not offer the same handles as other forces. Electricity has positive and negative charges. Magnetism has north and south poles. With these dualities, nature allows us to cancel, reverse, and shape the forces into useful forms. But gravity knows only one kind of charge, mass and energy, and no negative mass has ever been found. To cancel gravity as one cancels electricity would require a form of matter that falls upward, repelled by the Earth rather than attracted to it. Such matter remains entirely hypothetical, perhaps impossible. That absence of a counterpart is one reason why humanity, for all its genius, still falls down when it slips. Still, there is hope hidden in history. For centuries, people believed flight was impossible because the mathematics seemed cruel. The weight of a person, the strength of materials, the lift of air, all seemed to conspire against sustained flight. Yet engineers and inventors learned to exploit principles that were not obvious at first glance. The airplane is not a triumph over gravity, but a clever use of air pressure and forward motion to produce lift. In the same way, it is conceivable that humanity may one day discover a principle that allows gravity to be shaped or countered, not by brute force, but by subtle exploitation of some deeper rule of physics. The key is not to believe blindly, but to investigate carefully, to test ideas against nature, and to remain open to surprises. The myths of the past, though inaccurate, served an important purpose. They kept the dream alive through centuries, when science had no language to explain it. They carried forward the intuition that something was missing, that there must be more to the story of weight than the feeling of heaviness in our bones. Now science gives us sharper tools. We know how to measure the acceleration of falling objects with exquisite precision. We know how to test theories of space-time by observing the motion of planets, the bending of starlight, and the ripples of gravitational waves. We know how to build instruments that can detect distortions in space-time smaller than the width of an atom. These tools have not yet delivered a way to control gravity, but they have revealed its nature more clearly than ever before. And so the story of humanity's dream of defying gravity becomes more complex. It is no longer a tale of magic carpets or winged gods. It is a tale of centuries of observation, theory, and experiment. It is a tale of failures that sharpened our understanding, of false claims that taught us caution, of triumphs that revealed just how far precision can go. The dream is not dead. It has simply matured. Today, when scientists ask whether gravity can be controlled, they do not expect a switch that cancels weight. They expect to find subtle principles buried in the equations of relativity or quantum theory, principles that may one day allow manipulation not in mythic leaps but in careful steps. Before we imagine what those steps might be, we must pause and ask the central question: what is gravity, truly? Is it a force that reaches across space like a tether? Is it a curvature of space-time itself, as Einstein suggested? Is it an emergent effect, a kind of thermodynamic bookkeeping that arises from deeper laws of information? These are not idle puzzles. The answer will determine whether gravity can be shaped at all, and if so, how. To reach that answer, we must turn to history's most profound scientific revolutions, beginning with the quiet genius of Isaac Newton and culminating with the deep insights of Albert Einstein. That is where the journey leads next. The dream of overcoming gravity is older than memory, but it grows sharper when placed beside the discoveries of science. The myths and stories that carried our ancestors through long nights under the stars gave them visions of ascent, but it was the first real glimpses of physical law that turned imagination into a project. When Galileo dropped spheres from the Leaning Tower of Pisa, he showed that the pull of Earth worked on all masses equally. When Kepler wrote his laws of planetary motion, he revealed that the same invisible tether held planets in orbit as held apples to the ground. These were hints that a universal principle was at work, something deeper than folklore. The stage was set for Newton to write his law of universal gravitation, a formula that could describe with one stroke both the fall of stones and the dance of worlds. For the first time, humanity did not just dream of flight, it possessed an equation that explained why the dream was so difficult to reach. And yet the equation did not kill the dream. Instead, it transformed it. By showing that gravity had rules, Newton implied that those rules might be understood, perhaps even harnessed. Rockets are nothing more than Newton's third law made manifest, pushing mass backward to propel mass forward. Orbits are nothing more than carefully chosen trajectories within Newton's framework, paths that fall forever without ever striking the ground. In this sense, every satellite, every spacecraft, every lunar landing is part of the long story of our negotiation with gravity. We do not cancel it, we do not command it, but we learn to work with it, to ride it like a current in the sea. The difficulty is that these victories are all conditional. They rely on immense expenditure of energy, precise engineering, and the acceptance that gravity itself remains unchanged. When a satellite circles Earth, gravity is not weaker there. The astronaut floating inside feels weightless only because both he and his craft are falling together. It is an illusion born of motion, not a true manipulation of the fundamental force. Even the mightiest rocket does not change gravity. It simply resists it long enough to reach a path where motion does the rest. For all our ingenuity, we are still playing within the rules, not rewriting them. But humans are not satisfied with illusions. We want the real thing. That is why stories of anti-gravity captivate us so deeply. They offer not just an extension of what we already do, but a rupture, a genuine overturning of the order we know. To picture a ship hovering without thrust is to picture a physics that is different, one where the rules bend to human will. This desire reveals something about our psychology. Gravity is not only a physical force, it is also a symbol of limitation. It is the hand that presses us down when we try to leap. It is the invisible chain that binds us to a single planet in a vast universe. To master gravity would be to declare independence from those limitations. It would be the ultimate act of liberation, not only physical but also cultural, a promise that nothing in nature could confine us any longer. And yet this dream collides with the sobering truth of physics. When we measure gravity, we find no cracks in its armor. The equivalence principle tells us that acceleration and gravity are indistinguishable, that every object falls the same way, regardless of its mass or composition. This has been tested with exquisite precision, from laboratory experiments to observations of celestial bodies. General relativity tells us that gravity is not a force in the traditional sense at all, but the curvature of space-time itself, a fabric that bends around mass and energy. This view is harder to imagine than Newton's, but it has passed every test placed before it, from the bending of starlight during eclipses to the timing of pulsars and the detection of gravitational waves. If gravity is geometry, then to manipulate it would mean to sculpt space-time itself, a task so far beyond our reach that it borders on the miraculous. Still, the story is not finished. The 20th century showed that nature hides surprises, from quantum mechanics to nuclear energy. Fields once thought immutable revealed hidden rules that could be exploited. It is possible that gravity too hides secrets not yet uncovered, principles that will open doors we cannot yet imagine. But until those doors are found, the dream remains suspended between myth and science, between the soaring visions of storytellers and the measured caution of physicists. And so we arrive at the threshold. We have traced the dream of defying gravity from its mythic roots to its scientific framing. We have seen how it has shaped our imagination, our engineering, and our sense of what might be possible. But the question remains unresolved. Is gravity a force that can be bent to our will, or is it the final boundary we must accept? To even begin to answer, we must understand it in its own terms. We must look more closely at the law Newton wrote, at the vision Einstein offered, and at the experiments that continue to probe its limits. Only then can we speak with honesty about manipulation. Only then can we separate fantasy from possibility. The dream will not be satisfied until we know. And so, to move forward, we must ask the simplest, most difficult question. What is gravity? When Isaac Newton first wrote the law of universal gravitation, he gave humanity a tool of astonishing power, a single equation that explained why apples fall and why planets circle the Sunday. To grasp its importance, imagine the 17th century world in which Newton lived. Astronomy was flourishing with careful observations of planets by Tycho Brahe and Johannes Kepler. Kepler's laws described how planets moved, tracing out ellipses and obeying simple timing rules. Yet no one knew why. On Earth, stones fell, rivers flowed downhill, and cannonballs arced across the sky. But no one saw the connection between terrestrial motion and celestial motion. Newton's insight was to unify them. He proposed that the same invisible pull that made an apple drop to the ground also reached across the void to keep the moon in orbit. With this unification, The heavens and the earth were no longer separate realms. They were bound by one law. Newton's law is simple to say. Every mass attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. In other words, double the mass and the pull doubles. Double the distance and the pull shrinks to a quarter. With this one rule, Newton could explain the tides, the orbits of planets, the paths of comets, even the subtle wobble of the Earth as it danced with the moon. It was breathtaking in its scope. The universe suddenly appeared as a clockwork machine, precise and predictable. But Newton himself admitted a mystery. He could write the equation, he could calculate its results, but he could not say how gravity worked. He spoke of action at a distance, of one body pulling another instantly across empty space. To his contemporaries, this was unsettling. How could matter exert influence with no medium between? Newton did not pretend to know. He offered the law as a description, not an explanation. For centuries, this was enough. Engineers built bridges, navigators charted courses, astronomers predicted eclipses, all using Newton's equations. Gravity was reliable even if its mechanism was hidden. By the 19th century, however, cracks began to appear. Precise measurements showed that the orbit of Mercury shifted in a way Newton's law could not fully explain. Light, too, seemed unaffected by Newtonian gravity, even though it carried energy, and thus, one would think, should be influenced by mass. Scientists searched for hidden planets or subtle corrections, but the deeper answer came only in the early 20th century, when Albert Einstein proposed a radical new vision. Einstein's general relativity redefined gravity, not as a force at all, but as the curvature of space-time. To understand this, picture space-time as a flexible sheet. Place a heavy ball in the center, and the sheet dips. Place a smaller ball nearby, and it rolls toward the heavy one, not because the larger ball pulls it, but because the sheet curves beneath it. In the same way, mass and energy curve space-time, and objects follow the curved paths. What we feel as the pull of gravity is really the geometry of the universe guiding motion. This shift from force to geometry changed everything. It explained why Mercury's orbit precessed, because space-time near the Sun is more curved than Newton's law predicted. It explained how light bends around stars, because light follows the straightest possible path through curved space-time, which to us looks like bending. It predicted black holes, regions where space-time is curved so steeply that not even light can escape. It predicted gravitational waves, ripples in space-time itself, that travel across the universe. Time and again, experiments confirmed Einstein's vision. Central to general relativity is the equivalence principle. Einstein realized that acceleration and gravity are, to astonishing precision, indistinguishable. If you are inside a closed room and feel yourself pressed to the floor, you cannot tell whether you are on Earth experiencing gravity or whether the room is a spaceship accelerating through deep space. The effects are the same. This principle is not just philosophical, it is the bedrock of relativity, leading directly to the idea that gravity is geometry. The indistinguishability of acceleration and gravitation is why clocks run more slowly on Earth's surface than in orbit, why GPS satellites must correct for relativistic effects, and why space-time itself is the stage upon which physics unfolds. For ordinary life, Newton's equations remain perfectly useful. They are easier to calculate and accurate enough for bridges, airplanes, and most space missions. But when precision matters, or when gravity is extreme, Einstein's relativity is required. The universe follows his geometry, not Newton's force. In this sense, our understanding of gravity has matured from rule to structure, from description to deeper insight. Yet even Einstein's vision leaves questions. Why should mass curve spacetime at all? What is the fabric of spacetime made of, if anything? How does gravity fit with quantum mechanics, which describes the other forces of nature with particles and fields? The equivalence principle suggests a unity, but unification has eluded us. Some physicists seek the graviton, a hypothetical particle that would mediate gravitational interactions in the quantum picture. Others propose that gravity may not be fundamental at all, but emergent from deeper principles of entropy and information. What is certain is that to manipulate gravity, we must understand it at this deeper level. If it is geometry, then control means sculpting space-time. If it is a particle field, then control means producing or guiding gravitons. If it is emergent, then perhaps manipulation means reshaping the hidden information from which it arises. Each possibility points to a different frontier, but before we cross those frontiers, we must be clear about the foundations. Gravity, as we know it today, is both simple and profound. It is the falling apple and the orbiting planet. It is the curve of starlight and the slow ticking of a clock near Earth's surface. It is the collapse of stars and the expansion of the universe itself. To think of controlling it is to think of mastering the very stage upon which all existence plays. But to know whether this dream is real, we must first accept what gravity is and what it is not. Only then can we ask what might be changed. And so, the next step in our journey is to consider what manipulation of gravity already occurs, not by our hands, but by nature itself. Stars, planets, and black holes move mass and energy in ways that bend space-time on scales we can only observe. Even human instruments, delicate and precise, have begun to measure these curvatures. If we wish to imagine engineering gravity, we must first learn from the universe's own demonstrations. When Einstein unveiled general relativity, the world received not just a new theory, but an entirely new way of perceiving reality. To think of gravity as geometry, rather than force, is to abandon centuries of intuition. We grow up feeling that objects fall because they are pulled, that the earth tugs on the apple, that the sun tugs on the earth. Relativity insists otherwise. The apple falls because space-time is bent around Earth, and the path the apple follows is the straightest path available in that curved geometry. To accept this requires a shift in imagination, a willingness to picture reality not as a stage of empty space, but as a fabric that can warp, stretch, and ripple. This concept is made clearer by the equivalence principle. Imagine standing in a sealed room. You feel pressed to the floor with a familiar heaviness. But are you standing on Earth, held down by gravity? Or are you aboard a spaceship accelerating through the void at exactly 9.8 meters per second squared? Relativity says you cannot tell. Both scenarios produce identical sensations. To the apple that falls from a branch, the experience is indistinguishable from floating in a rocket as the rocket accelerates upward. This principle, simple yet profound, was Einstein's key insight, the doorway to the curved universe. The power of general relativity lies in its predictive accuracy. When scientists calculated the precession of Mercury's orbit using Newton's laws, the numbers fell short. Mercury, the innermost planet, drifted slightly out of sync, completing its path around the Sun with a rotation of its ellipse that could not be explained by Newton. General relativity accounted for this discrepancy perfectly. During a solar eclipse in 1919, astronomers measured the deflection of starlight passing near the sundial. The results matched Einstein's predictions, confirming that light itself followed the curves of space-time. Later, discoveries of pulsars, binary stars, and eventually gravitational waves all strengthened the theory's foundation. It is easy to forget how radical this was. To declare that space and time themselves could bend was to overturn the very notions of absolute reality. Newton's universe had been a stage upon which matter played. Einstein's universe was a living fabric, shaped by the actors upon it. And unlike stage scenery, this fabric was not passive. It responded dynamically. When two black holes spiral together, they shake space-time, sending out ripples that travel across the cosmos. Billions of years later, those ripples pass through Earth, stretching and squeezing detectors on the ground. Instruments like LIGO have measured those changes, displacements smaller than the width of a proton, yet undeniably real. We have, in effect, listened to space-time itself, ringing like a vast, invisible drum. All of this brings us closer to the central question of manipulation. If gravity is geometry, then control of gravity would mean reshaping spacetime at will. We already know nature can do this. Stars bend the paths of nearby planets. Black holes twist the very fabric around them. Galaxies lens the light of objects behind them. The cosmos is filled with examples of spacetime being sculpted. But humans are small players. Our mass is trivial compared to stars. The bending we produce is unimaginably faint. Even our mightiest constructions, skyscrapers or mountains moved by human labor, barely dent spacetime. For practical purposes, the curvature we generate is negligible. And yet, relativity reminds us that no curvature is ever truly zero. Every bit of mass contributes. A person sitting in a chair bends spacetime, however minutely. Two people walking past one another influence each other's paths not only with eyes and words but with gravity, though the effect is vanishingly small. This universality hints at the tantalizing possibility that manipulation is not about finding a new principle, but about finding a way to amplify the one we already have. Could there be techniques to enhance our gravitational influence, or to mimic the way cosmic bodies bend spacetime without requiring cosmic masses? That remains an open question. Meanwhile, general relativity leaves us with mysteries still unsolved. The equations describe how spacetime curves, but they do not explain why mass has the ability to curve it, nor do they connect smoothly with the rules of quantum mechanics, which govern the very small. Attempts to quantize gravity, to imagine a particle called the graviton that carries the interaction, have not yet yielded experimental confirmation. At the frontier, physics still hesitates between treating gravity as a smooth fabric and treating it as a field composed of quanta. Until this divide is bridged, our understanding remains incomplete. For engineers and dreamers, however, the practical question is sharper. Even without knowing the ultimate foundation, can we learn to bend gravity in ways useful for technology? Einstein's equations allow exotic solutions, like wormholes and warp bubbles, but they require negative energy or matter with properties never observed. Still, the equations themselves do not forbid such things outright. This is where imagination presses against theory. We must tread carefully, balancing possibility with plausibility. The nature of gravity, as we see it now, is layered. On the everyday scale, Newton's law provides accurate predictions. On the cosmic scale, Einstein's geometry takes over. At the quantum scale, the true picture remains hidden. For the purpose of manipulation, all three perspectives matter. Newton shows us how to navigate orbits. Einstein shows us how mass shapes spacetime. And quantum theory hints that the force may not be fundamental at all. The interplay of these views is what makes gravity both fascinating and frustrating. To move forward in our story, we must consider what manipulation of gravity already exists, not in speculative technology, but in the real world. Planets and stars manipulate it by their sheer presence, shifting trajectories of other bodies. Humans have measured frame dragging, where Earth's rotation twists local spacetime. We have detected gravitational waves, disturbances that prove spacetime can be stirred. These examples may not be engineering feats, but they are evidence that manipulation in some form is real, even if it is on scales far beyond our control. And so, we reach another threshold. The question is no longer only what gravity is, but what forms of control already exist in nature. If the universe itself demonstrates gravity's malleability, can humans hope to replicate or harness these demonstrations? The next step is to examine the gravity we already manipulate, sometimes indirectly, sometimes unintentionally, but always within the bounds of the laws we know. The story of gravity has now carried us from Newton's equation to Einstein's curved universe, from the falling apple to the rippling of spacetime, across billions of light years. Yet to pause here would be incomplete, for the very questions raised by relativity lead directly to new puzzles. If gravity is curvature, what is it that curves? If space and time can bend, stretch, and ripple, are they made of something deeper, some hidden structure beneath the surface? And if so, is there a way to reach into that structure and change it? These are not idle questions. They sit at the crossroads of physics, where classical certainty meets quantum strangeness. where our best equations still leave shadows unexplored. The difficulty begins with the fact that general relativity and quantum mechanics are, to this day, uneasy companions. Quantum theory describes the world of the small, with particles and probabilities. Electromagnetism, for example, is carried by photons, tiny quanta of light that transmit force. The nuclear forces have their own carrier particles. Gravity, if it fits the same pattern, should have a carrier too, a hypothetical particle known as the graviton. The graviton has never been observed. If it exists, it must be so weakly interacting that no detector yet built could hope to capture it. And yet, in principle, it would be the key to describing gravity in quantum terms. Without it, relativity and quantum mechanics remain separate, two towering pillars of physics with no bridge between them. The search for that bridge defines much of modern theoretical physics. Some approaches imagine strings vibrating in higher dimensions, with gravity emerging naturally from their geometry. Others suggest holographic principles, where the information content of space-time gives rise to the gravitational field. Still others, like Eric Valindé's ideas of emergent gravity, propose that what we call gravity is not fundamental at all, but a side effect of entropy and information flow. These theories differ in detail, but share a common implication. If gravity is not fundamental, if it is built from something deeper, then perhaps manipulation will not come from pushing on mass or energy directly, but from controlling the hidden ingredients that generate the phenomenon. For now, these remain speculations. What experiments have confirmed is more grounded, and it is no less astonishing. Gravity can be measured with extraordinary precision. Drop towers, torsion balances, satellite orbits, and atomic clocks all confirm the equivalence principle to parts in trillions. Gravitational waves have been detected, their patterns matching predictions with uncanny accuracy. Frame dragging, the twisting of space-time by Earth's rotation, has been measured by satellites like Gravity Probe B. Each of these is not only a triumph of theory, but a demonstration that space-time itself can be influenced. The influence is faint, but it is real. These experiments sharpen the line between dream and reality. They tell us that gravity can be changed, but only by moving mass or energy. When two neutron stars collide, space-time shakes. When a planet orbits, space-time curves. When a massive body spins, it drags the fabric around it. These are manipulations, but they are not under human control. They are the universe's own demonstrations, cosmic in scale. For humans to join in, to command gravity as easily as electricity, would require an amplification we do not yet know how to achieve. And yet the question will not go away. Gravity is too central, too powerful, too entwined with our existence for curiosity to stop. Even if we never learn to cancel it, understanding its nature is itself a form of power. Already, our grasp of relativity shapes technologies we depend on. Without relativistic corrections, GPS satellites would drift out of sync, navigation would fail, and modern society would stumble. This is manipulation at the level of knowledge, not control, but it shows how even abstract theory can become practical. If one day new principles emerge, their impact could be even greater. So the journey continues. We began with myths of levitation and chariots, passed through Newton's law of attraction, and entered Einstein's world of curved space-time. Along the way, we have seen how gravity defines the structure of the cosmos, and how it resists every attempt to be simplified. What lies ahead is the exploration of whether these laws allow manipulation beyond what nature already shows us. Can the universe's grand demonstrations be scaled down, engineered, and turned into tools, or are they forever beyond our reach? To answer, we must now turn to the next step, examining the gravity we already manipulate, sometimes by accident, sometimes by design, and always with awe at the scale of the challenge. When people ask whether humanity has ever manipulated gravity, the first instinct is to say no, that gravity is immutable. that only nature herself can bend space-time. But the truth is more subtle. Every time we move mass, we change the gravitational field of the universe, even if only by an imperceptible amount. It is not the dramatic anti-gravity machines of fiction, but it is manipulation nonetheless. The difference lies in scale. A mountain, carved by human labor, changes Earth's gravity field, but the effect is so small, it can only be measured by the most sensitive instruments. A skyscraper rising in a city adds to the planet's curvature, but the change is negligible. And yet, in principle, these are real manipulations. Gravity is universal, and it never ignores mass, no matter how small. The cosmos shows us what true manipulation looks like. Planets bend the paths of comets, steering icy wanderers into new orbits. Stars sculpt the space around them so that light itself curves, creating gravitational lensing visible across billions of light years. Black holes demonstrate the ultimate manipulation, warping space-time into wells so deep that not even light can escape. These are natural engineers of gravity, reshaping the universe on scales that dwarf our imaginations. Compared to them, our influence is a whisper in a storm. But that whisper is still there, measurable, real, and increasingly within the reach of our instruments. Consider frame dragging, a prediction of general relativity. When a massive body rotates, it twists the fabric of space-time around it. Earth, spinning on its axis, performs this cosmic trick. In 2004, NASA's Gravity Probe B mission placed ultra-precise gyroscopes in orbit to test the effect. After years of painstaking measurement, the results confirmed that Earth does indeed drag space-time by a tiny angle, just as Einstein predicted. Though we did not cause the dragging, we measured it. And in doing so, we participated in the first demonstrations of gravity's subtle malleability. Measuring is not the same as controlling, but it is a step toward understanding how space-time itself can be shaped. Even more dramatic is the detection of gravitational waves. When two massive objects, such as black holes or neutron stars, spiral together, they disturb space-time, sending ripples outward, like waves on a pond. These ripples travel across the cosmos, stretching and squeezing everything in their path. For decades, scientists debated whether these waves were real or just mathematical curiosities. In September of 2015, the LIGO Observatory detected them directly. Two black holes had merged over 1 billion light-years away, and the resulting waves traveled across space and reached Earth, altering the length of LIGO's detectors by less than the width of a proton. It was a cosmic whisper, faint but undeniable. With that detection, we confirmed not only that space-time can ripple, but that humans can build machines sensitive enough to feel the tremors of the universe itself. To call this manipulation may seem like stretching the term. After all, we did not create the waves, we merely observed them. But observation is the beginning of mastery. The first step in controlling any force of nature is to measure it, to detect it, to understand its patterns. Electricity was once a curiosity, sparks dancing on amber rubbed with fur. Only after careful measurement and theory did it become the engine of civilization. In the same way, gravitational waves may one day be more than cosmic whispers. Some scientists speculate that in a far future, technologies might be built to generate detectable waves, perhaps even to transmit information through space-time itself. This remains speculative, but the principle is sound. If black holes can ring like bells, then in theory, so might machines of our own. There are other, subtler manipulations already within our reach. Satellites orbit Earth in carefully chosen paths that exploit the balance of gravitational pull and orbital speed. By placing them at precise altitudes, we create geostationary orbits, where the satellite hovers motionless above a single point on Earth's surface. These orbits are not natural. They exist because human engineers designed them, using Newton's and Einstein's equations to bend trajectories to our will. Spacecraft use gravitational assists, slingshot maneuvers around planets, to gain speed without expending fuel. Here we are not only resisting gravity, but using it, redirecting its pull into propulsion. These are genuine manipulations, clever exploitations of the laws that bind us. Still, the dream of direct control remains distant. We cannot turn gravity off. We cannot reverse it. We cannot shield against it. Every experiment that claimed such results, from rotating superconductors to anti-gravity devices, has failed replication. The gravity we manipulate today is indirect, either by moving mass or by navigating space-time with precision. But this does not make it meaningless. It makes it the foundation upon which any future discovery must build. The lesson is clear. Nature herself shows us that gravity is pliable. We have witnessed planets bend comets, stars lens light, and black holes ripple space-time. We have measured Earth's subtle frame dragging and detected the faintest tremors of gravitational waves. We have used orbits and slingshots to redirect motion, exploiting gravity rather than fighting it. Each of these steps is part of the story of manipulation, not yet mastery but more than myth. The challenge ahead is to ask whether humanity can move beyond observation and exploitation into true engineering. Can we find methods to sculpt space-time deliberately, to bend gravity on command, not just measure its dance? The next step in our journey is to confront the search for the graviton, the hypothetical quantum of gravity. For if gravity has a particle, then it is a force like any other, with carriers that might be created, guided, or manipulated. If no particle exists, then perhaps gravity is something else entirely, something emergent and intangible. In either case, the answer will determine the path toward control. To know whether gravity can be manipulated, we must first know what it is made of at the smallest scales. That is where the story turns next. The idea that humanity already manipulates gravity may seem bold, but it is grounded in reality. Whenever we move mass, we shift the balance of the gravitational field around us. Of course, the scale is microscopic compared to the cosmos, but the principle holds. Think of Earth itself, a planet whose oceans rise and fall daily not from some hidden rhythm of the water but from the moon's pull. The tides are perhaps the most ancient and visible example of natural gravity manipulation. The moon moves, and the oceans answer, swelling on the side nearest the moon and the side farthest away. Early sailors charted their courses with tides in mind, long before they understood their cause. Even now, entire coastlines live by the rhythm of this ceaseless tug. Planets do the same to one another on far greater scales. Jupiter, with its immense mass, shepherds comets and asteroids, pulling them into orbits or ejecting them entirely from the solar system. Without Jupiter's gravitational dominance, Earth might face far more catastrophic impacts. Here, gravity acts as both protector and predator, shaping the history of life. At the most extreme, black holes show us gravity's ultimate grip, bending space-time so steeply that escape becomes impossible. These cosmic structures are reminders that the very laws we hope to bend are already being bent by nature in ways beyond comprehension. Humanity, with our tools and intellect, has learned to play with these forces in subtler ways. Consider the precision of satellite navigation. A spacecraft leaving Earth for another planet does not simply fire its engines and fly in a straight line. Instead, it threads a path through the solar system, using gravitational assists. By swinging past planets, it borrows momentum, stealing a little of their orbital energy and flinging itself forward at higher speed. The Voyager probes use such maneuvers to escape the solar system entirely, an achievement made possible only by a deep understanding of how to exploit the gravity of worlds. This is manipulation, not in the sense of commanding gravity, but in using it as a tool, turning what once was an obstacle into an ally. We have also detected phenomena that show how mass and motion manipulate space-time in ways barely perceptible but profoundly real. Frame dragging is one such effect. Earth's rotation twists space-time ever so slightly, and we can measure it with gyroscopes sensitive enough to detect a change in angle smaller than the width of a human hair over a year. The Gravity Probe B mission confirmed this twisting, a triumph of engineering that required nearly perfect spheres spinning in the vacuum of space. Though Earth performs the dragging, it was human determination that revealed it. In this sense, we participated in measuring a manipulation of space-time that had long been invisible. Then came the discovery of gravitational waves, ripples in space-time caused by cataclysmic events such as the collision of black holes. For decades, these waves existed only in equations, whispers of possibility. Yet in 2015, instruments on Earth recorded their arrival. Faint tremors traveling across the cosmos for over 1 billion years. The detectors, LIGO's massive interferometers, used beams of light stretched along kilometers of vacuum tunnels to measure distortions smaller than a proton's width. With that detection, we confirmed that space-time is not fixed but dynamic, that it can be stirred, shaken, and set ringing like a drum. This was not our manipulation, but it was proof that manipulation is possible, that space-time is not immovable but pliable. Even in more practical terms, humans shape their lives around subtle gravitational effects. We build artificial gravity in spacecraft by rotating them, using acceleration to mimic the pull of Earth. Astronauts train in centrifuges, feeling their weight increase as the spinning chamber pushes them against the seat. Though this is not true gravity, it is a clever imitation, and it demonstrates that human ingenuity can provide substitutes when nature refuses to yield. Similarly, we exploit orbits to maintain satellites in precise positions, ensuring communication, navigation, and observation. These satellites exist only because we have mastered the dance of gravity well enough to choreograph it. Still, these achievements remind us of the gap between dream and reality. We cannot yet bend space-time at will. We cannot produce gravitational waves with machines, only detect those born in cosmic violence. We cannot twist space-time deliberately, only measure Earth's slow dragging of it. We cannot shut gravity off, only use centrifugal tricks to mimic it. Our manipulations are indirect, partial, and always subject to the larger rules of nature. But they are real, and they hint at what might one day be possible. The question that follows naturally is whether we can ever go further. If nature can bend and twist space-time, why not us? If black holes can ring the universe with gravitational waves, could we ever build instruments to do the same on smaller scales? Could the subtle manipulations we already measure be amplified into engineering principles? The answers depend on the deepest structure of reality. If gravity has a quantum particle, then perhaps it can be generated and controlled, like photons. If gravity is emergent, then perhaps it can be altered by reshaping the information that gives rise to it. To move forward, we must now confront that frontier, the search for the graviton, the particle that may or may not exist, and whose discovery would decide whether gravity truly belongs with the other forces of nature. Humanity's current relationship with gravity is one of respect mixed with quiet ingenuity. We know that we cannot turn it off, yet we have found ways to bargain with it, to coax it into serving us. Consider the Hubble orbit. A spacecraft launched from Earth is not truly free of gravity. In fact, it is falling toward Earth at every moment. What saves it from crashing is its speed. It moves forward fast enough that as it falls, Earth curves away beneath it. The result is continuous free fall, a dance with gravity that looks like defiance, but is really cooperation. Astronauts floating in the International Space Station are not beyond gravity's reach. They are in its grasp completely, caught in an endless fall that just happens to miss the ground. This is manipulation in the sense of strategy, an exploitation of the rules without breaking them. Our species has also grown skilled at measuring gravity's tiniest nuances. Geophysicists use gravimeters to detect changes in density beneath Earth's surface, mapping underground structures, or following the rise of magma before a volcanic eruption. These instruments are so sensitive, they can register the difference in pull caused by a passing truck. In laboratories, Experiments with torsion balances measure the gravitational attraction between small objects, confirming Newton's law at scales where the pull is weaker than the weight of a dust mote. These measurements may seem technical, but they show something profound. We can now detect and account for gravitational changes at levels so subtle that earlier generations would never have believed they existed. To measure with such precision is to begin, in a sense, to manipulate. Knowledge itself is a form of control. Even our explorations beyond Earth rely on gravitational maneuvers that turn planets into tools. When the Voyager probes set out for the outer solar system, their journeys would have taken centuries without assistance. Instead, mission planners used the rare alignment of planets in the 1970s to design a grand tour. Each probe swung past Jupiter, Saturn, Uranus, and Neptune, stealing a fraction of each planet's momentum to speed onward. The planets hardly noticed the theft, but the spacecraft gained immense velocity. This method, the gravitational slingshot, is a clear example of humans using gravity, not as an obstacle, but as a resource. By understanding the equations, we persuaded planets to lend us their energy. Yet all these examples share one limitation. They rely on existing masses and motions. We do not create new gravitational effects. We harness the ones that are already there. To move beyond this stage, to become true engineers of gravity, would require generating curvature where none existed, sculpting space-time deliberately. That step has not yet been taken, but our current manipulations remind us that the universe allows such shaping in principle. After all, the difference between a stone and a star is only one of scale. Both bend space-time, one faintly, one dramatically. If scale is the only barrier, then perhaps technology may one day amplify our influence in ways we cannot yet imagine. For now, we must acknowledge the boundary between ambition and reality. We manipulate gravity by moving masses, by navigating orbits, by borrowing momentum, by measuring subtleties. We do not yet command it, but we also know that progress begins with small steps. Electricity was once only sparks and shocks before it became the engine of modern life. Nuclear power was once only theory before it became both weapon and energy source. Gravity too may follow such a path, from faint measurements to profound control. Whether that path is short or impossibly long remains to be seen. And so, the story leads naturally to the quantum frontier. If gravity has a particle, the graviton, then it belongs fully to the family of forces described by quantum field theory. If such a particle exists, we might one day learn to generate, detect, and manipulate it. If it does not, then gravity is something stranger, something that may not yield to control in the ways we expect. The search for the graviton is more than a scientific curiosity. It is the deciding question for whether gravity will ever be tamed. To explore this, we must now leave the realm of orbits and slingshots and enter the uncertain terrain of quantum gravity, where particles may or may not exist, and where our understanding of reality itself is at stake. The elegance of general relativity has carried us far, yet it leaves us staring at a chasm. On one side is the smooth fabric of space-time, bending and rippling as Einstein described. On the other is the quantum world, where all forces are mediated by particles, where interactions come in discrete quanta. Electricity has its photon. The strong nuclear force has gluons. The weak nuclear force has W and Z bosons. Gravity, if it belongs in this family, should have its own carrier particle, the graviton. But here is the trouble. No graviton has ever been detected, and many physicists suspect it may never be. To understand why, consider the scale of gravity's weakness. The electromagnetic force is so strong that a single small magnet can lift a paperclip against the pull of the entire Earth. Gravity, by comparison, is feeble beyond imagination. This weakness makes gravitons nearly impossible to observe. If they exist, they must interact so faintly with matter that even the most sensitive detectors could wait longer than the age of the universe without recording a single event. Searching for them is like trying to hear a single raindrop in the middle of a thunderstorm. Still, theory compels us to imagine them. In quantum field theory, every force arises from an exchange of particles. If gravity is a force like any other, it should arise from gravitons, massless particles with spin 2. These properties are not arbitrary. They follow from the mathematics of how space-time symmetry works. A graviton would move at the speed of light, just as photons do, but it would carry the geometric influence of gravity, guiding the curvature of space-time at the smallest scales. Some indirect hints exist. Gravitational waves, already detected by LIGO, can be thought of as coherent waves of countless gravitons, just as a radio wave is a collective vibration of photons. The fact that we have measured these waves suggests that gravitons make sense as a mathematical tool, but detecting individual ones is another matter. Their energy is so faint that no experiment yet devised can hope to capture them. The challenge becomes sharper when we remember that relativity and quantum mechanics resist union. Relativity treats spacetime as smooth, continuous, and deterministic. Quantum mechanics treats reality as granular, probabilistic, and uncertain. When we try to quantize gravity, infinities appear in the equations, stubborn divergences that refuse to cancel. Other forces fit comfortably into quantum field theory. Gravity does not. The graviton may exist in theory, but the framework needed to house it remains incomplete. This difficulty has led to ambitious ideas. String theory suggests that particles are not points, but tiny vibrating strings, and that gravitons appear naturally as one of the string's vibrational modes. In this vision, gravity emerges elegantly, and the incompatibility with quantum mechanics dissolves. But string theory requires extra dimensions, mathematical spaces we cannot yet confirm, and so far, no direct experimental evidence supports it. Another approach is loop quantum gravity, which attempts to quantize spacetime itself, imagining the fabric not as smooth, but woven from tiny loops of quantum fields. In this framework, gravitons may not be fundamental, but approximate descriptions of deeper structures. The universe at the smallest scales might be a discrete lattice, like a network of interwoven threads. Gravity, then, would be the large-scale behavior of this weave. There are even more radical suggestions. Some physicists argue that gravity may not be fundamental at all. Eric Valinde has proposed that gravity is emergent, arising from the statistical behavior of microscopic degrees of freedom, much as temperature arises from the motion of molecules. In this view, searching for gravitons would be like searching for a particle of temperature. It simply does not exist, because gravity is not a fundamental force, but an emergent phenomenon. The implications are profound. If the graviton exists, then perhaps gravity can be treated like other forces, subject to control in principle, though the technical obstacles are immense. If it does not exist, then gravity is something else entirely, and any attempt to manipulate it must begin from that deeper reality. Either path demands answers, because without them, our dream of controlling gravity remains adrift. And yet, even without direct evidence, the search continues. Particle accelerators probe higher energies, looking for deviations that might hint at gravitons. Cosmologists study the cosmic microwave background, hoping to see imprints of primordial gravitational waves, faint ripples from the universe's earliest moments. Theorists push forward, refining models, hunting for consistency, searching for ways to merge relativity with quantum mechanics. Each step is small, uncertain, and slow, but together they form the frontier of one of the greatest scientific quests. This frontier is not only about science, it is about possibility. If gravitons exist, they are unimaginably faint, yet they could open doors to control at scales we cannot yet envision. Imagine a device that could generate coherent gravitons the way a laser generates photons. Such a device would bend space-time deliberately, creating ripples not from colliding black holes, but from engineered instruments. This is speculative, fantastical even, but it is the logical extension of accepting the graviton as real. If, on the other hand, gravity is emergent, then our task is to discover the hidden principles from which it arises. In that case, control may not come from particles, but from manipulating information, entropy, or other deep structures. This too is speculative, but it may one day be testable. Either way, the question of the graviton is central, because it decides the very nature of the path ahead. The search for gravitons has not yet yielded discovery, but it has forced us to confront the deepest questions of physics. What is space-time made of? Is gravity fundamental or emergent? Can we quantize the universe, or must we rethink the framework itself? These questions are not merely academic. They are the foundations upon which any dream of gravity manipulation must rest. Until we know whether the graviton is real, the possibility of engineering gravity remains suspended between promise and mystery. And so the path leads us further still, into the possibility that gravity may be an illusion, not a true force, but a shadow cast by deeper rules. To explore that frontier, we must follow the ideas of emergent gravity, where the cosmos itself whispers that space-time may be woven from information, and that gravity is only the echo of entropy. The idea of the graviton may sound simple enough, but when physicists attempt to give it mathematical life, they quickly encounter paradoxes. In quantum field theory, particles interact by exchanging force carriers. Electrons repel one another by tossing photons back and forth. Quarks cling together through the grip of gluons. If gravity fits this framework, then any two masses should feel their attraction through the constant trade of gravitons. The problem is that gravity does not play by the same rules. When physicists write down the equations for gravitons, the mathematics explodes with infinities that cannot be renormalized, meaning they cannot be tidied up into finite predictions the way other forces can. Gravity, in the language of quantum field theory, misbehaves. This misbehavior is one reason physicists have spent decades chasing theories beyond the standard model. String theory offers one hope. By replacing particles with tiny vibrating strings, it smooths out the infinities and naturally includes a particle with the properties of the graviton. In string theory's higher dimensional universe, gravity emerges not as an outlier, but as a natural consequence. Yet the theory is so vast and so flexible that critics argue it explains everything and nothing. Without experimental evidence of extra dimensions or supersymmetric partners, string theory remains elegant, but unproven. Another path, loop quantum gravity, takes a more minimalist approach. Instead of imagining strings, it quantizes space-time itself, slicing the fabric into tiny discrete chunks. In this vision, geometry is made of loops woven into a network at the smallest scales. Gravitons may appear in this picture as approximations, like ripples moving across a woven fabric. But again, experimental confirmation is lacking, and without evidence, the picture remains hypothetical. Some have turned to cosmology for clues. The universe itself may be the greatest experiment ever conducted. During the earliest fractions of a second after the Big Bang, quantum fluctuations should have produced gravitational waves, faint imprints still etched into the cosmic microwave background. Detecting those imprints would be indirect evidence for gravitons. Experiments like BICEP and the Planck satellite have searched for these signatures, finding tantalizing hints, but no definitive proof. The hunt continues, with new detectors scanning the heavens for the polarization patterns that would confirm a primordial gravitational wave background. Meanwhile, particle accelerators like the Large Hadron Collider probe high energies where gravity might reveal itself. Some models suggest that gravitons could slip into extra dimensions, leaving behind missing energy signatures in the collisions. So far, no such signatures have been found. The collider has discovered the Higgs boson, but no evidence for gravitons. Yet the absence of proof is not proof of absence. Gravity is so weak compared to other forces that it may hide its secrets at scales forever beyond our reach, and so physicists live with uncertainty. Some believe gravitons exist, but will never be detected, too faint for any experiment. Others suspect gravity is not fundamental, and gravitons are illusions, like mirages in a desert. Still, others insist that a future theory, not yet written, will resolve the paradoxes and show us how gravity fits with quantum mechanics. Each camp agrees on one point: without understanding gravity at the quantum level, physics remains incomplete. The implications for manipulation are stark. If gravitons are real and one day controllable, then in principle, we could generate gravitational fields the way we generate electromagnetic fields. Imagine a gravity laser, a coherent beam of gravitons bending space-time at will. This is pure speculation, but it follows the same logic that turned photons into lasers, radio, and fiber optics. If, however, gravitons are not real, then gravity may never yield to particle-based engineering. It may require entirely new strategies, manipulating information, or geometry itself, rather than particles. This uncertainty fuels both frustration and wonder. The search for gravitons is not only about adding one more particle to the roster, it is about deciding whether gravity belongs in the same family as the other forces or whether it is something stranger. The answer will not only determine our understanding of the universe, but also set the stage for whether humanity might ever learn to bend space-time deliberately. For now, the graviton remains elusive, a ghost in the equations, a particle that may exist only as a useful fiction, but the very act of searching pushes science forward. Every failed experiment narrows the possibilities. Every new observation refines the models. Each step brings us closer to knowing whether gravity can be placed alongside light and matter in the great quantum tapestry, or whether it stands apart, something emergent, something not yet understood. And so we arrive at the threshold of an even more unsettling possibility. What if gravity is not a fundamental force at all? What if it is a mirage, an emergent phenomenon rising from the collective behavior of deeper laws? If that is true, then searching for gravitons may be like searching for atoms of sound. The sound is real, but its atoms are not. To explore this possibility, we must step into the realm of emergent gravity, where entropy and information may be the true architects of the universe, and where control of gravity might mean control of knowledge itself. The quest for gravitons has become a kind of mirror, reflecting both the brilliance and the limitations of modern physics. On one side stands the elegance of mathematics, insisting that if all other forces are quantized, gravity should be as well. On the other side stands stubborn reality, where every experiment returns silence, as though the universe is reminding us that its deepest secrets will not be given cheaply. This silence is not without meaning. It forces us to question whether our assumptions are correct, whether we are asking the right questions, or whether gravity belongs in a category of its own. Imagine a future where technology has advanced so far that detectors can sense energies and interactions billions of times smaller than anything we measure today. Even in such a future, many physicists argue, gravitons might remain invisible. They are thought to interact so weakly with matter that to detect just one would require a detector the size of a planet, operating for longer than the current age of the universe. If this is true, then the graviton is a particle forever out of reach, knowable only through indirect reasoning. It would be as if we could describe lightning without ever feeling a spark. And yet, indirect evidence can be powerful. We have never seen a photon directly with our eyes, only the effects of countless photons together. We have never touched a gluon, yet particle accelerators and theoretical consistency demand its existence. If gravitational waves can be seen as oceans of gravitons moving in concert, then perhaps the graviton is as real as any particle we cannot isolate. The wave may be the chorus, the particle, the single voice, both describing the same music. This perspective leads to fascinating speculation. If one day humans learn to generate coherent waves of gravitons, perhaps by amplifying quantum fluctuations of space-time, we could, in principle, shape gravity. Such a device would not cancel weight like science fiction imagines, but it might create regions of altered curvature, bubbles of geometry engineered by design. These ideas remain far beyond practicality, but so too did nuclear energy or quantum computing in their earliest days. Science advances by imagining what seems impossible, then testing where imagination fails. On the other hand, if gravitons are fictions, if gravity is emergent rather than fundamental, then the dream of manipulating it through particle beams or graviton fields may vanish entirely. But this does not make control impossible. It shifts the battlefield. If gravity arises from entropy, information, or holographic principles, then perhaps control lies in manipulating those deeper layers. In that vision, to bend gravity would be to rewrite the hidden code of space-time itself, a project as astonishing as it is speculative. What matters is that the search, though unfinished, clarifies our position. We stand at the edge of a map where known physics gives way to mysteries that resist easy answers. The graviton, whether real or not, forces us to confront the incompleteness of our knowledge. It demands that we seek a theory that unites the smooth curves of relativity with the discrete quanta of the microscopic world. Until that theory is found, gravity will remain the outlier, the one force we cannot fit neatly into the puzzle. And so the chapter closes, not with resolution, but with a sharpened question. The graviton is either the faintest particle in existence or a phantom we chase in vain. Its discovery would confirm that gravity belongs to the quantum family, perhaps opening paths to control. Its absence would suggest that gravity is something altogether different, demanding a revolution in our understanding. In both cases, the dream of manipulating gravity depends on the answer. The next stage of our journey is to explore what happens if the graviton is not real, if gravity is not fundamental but emergent. Here we will enter the strange and provocative realm of theories that treat gravity as an illusion, a consequence of entropy, information, or the statistical behavior of microscopic degrees of freedom. To ask whether we can control gravity in that picture is to ask whether we can control the very flow of information in the universe. The quest for the graviton leads naturally into a stranger possibility, one that unsettles the very idea of what Gravity Island. For centuries we have treated gravity as fundamental, first as a mysterious pull across empty space, then as the curvature of space-time itself. But some physicists now suggest that gravity may not be fundamental at all. Instead, it might be emergent, a phenomenon that arises from deeper principles, much as temperature arises from the motion of molecules. In this picture, gravity is not a primary force of nature, but the shadow of more hidden laws. The idea of emergent gravity owes much to the work of Erik Verlinde, a Dutch theoretical physicist who proposed in the early 2010s that gravity could be explained as an entropic force. Entropy, the measure of disorder, is a cornerstone of thermodynamics. When heat flows, when gases spread out, when time moves in one direction rather than the other, entropy is at work. Verlinde argued that gravity might be similar, not a fundamental interaction, but a consequence of statistical behavior. According to his proposal, space-time itself contains information, and the movement of matter through it changes that information. Gravity, then, is the universe's way of balancing the books, ensuring that entropy and information evolve consistently. To imagine this, think of the surface of a pond. On the scale of water molecules, the pond is a chaotic storm of collisions. But at larger scales, the chaos smooths into ripples and waves, patterns that emerge from countless interactions below. The waves are real, they can be measured and surfed, but they are not fundamental. They are the consequence of deeper dynamics. Emergent gravity suggests that space-time and its curvature may be like those waves, visible patterns, produced by hidden degrees of freedom. If this is true, the implications are extraordinary. It would mean that our quest for gravitons is misguided, that no such particle exists, because there is nothing to carry. Gravity would not be mediated by an exchange particle, but by the statistical rules of information. It would also mean that to control gravity, one would not build graviton lasers, but would instead need to manipulate the information substrate of the universe. Such a task is as alien to us as manipulating individual molecules of a pond to sculpt its waves. But it is not unthinkable. Emergent gravity has also been proposed as a way to explain one of cosmology's deepest mysteries: dark matter. For decades, astronomers have measured the motions of galaxies and found that stars at their edges move faster than Newtonian and Einsteinian gravity predict. The usual explanation is that some invisible mass, called dark matter, provides the missing gravitational pull. Yet dark matter has never been detected directly. Verlinde suggested that these anomalies might not require dark matter at all, but instead arise naturally if gravity is emergent. In his framework, the way information is distributed in spacetime produces extra gravitational effects that mimic dark matter. This idea remains controversial. Many physicists remain skeptical, pointing out that dark matter explains more observations, from galaxy clusters to the cosmic microwave background. But the very fact that emergent gravity offers a rival explanation shows how radical the concept island. If proven, it would not only rewrite our understanding of galaxies but also recast gravity itself as a secondary phenomenon, a byproduct, rather than a cause. The unsettling consequence is that if gravity is emergent, then our dream of manipulating it must change. We cannot bend entropy directly any more than we can scoop up temperature with our hands. But we can influence entropy by manipulating its underlying components, just as we can change the temperature of water by heating or cooling the molecules within. If gravity is an illusion born from information, then perhaps the key lies in controlling information itself. Quantum computers, holographic principles, and theories like ADS, CFT already hint at ways the universe may encode reality. To control gravity in this vision is to rewrite the code. For now, these ideas remain speculative. Experiments have not yet confirmed or disproved emergent gravity. Verlinde's predictions work well for some galactic observations, but struggle with others. The debate is ongoing, a reminder that physics is a living science where bold ideas must wrestle with evidence. Still, emergent gravity has already done something important. It has shown that even the most basic concepts, like the force that holds us to the ground, may not be what they seem, and so we arrive at a new frontier. If gravity is emergent, then the very question of manipulation becomes more complex. It is no longer about controlling a force, but about controlling the deeper fabric of information and entropy that gives rise to it. This frontier is speculative, daring, and uncertain, but it is where the search must go. The next step is to follow these implications further, to see what it means for the cosmos, for dark matter, and for our dream of reshaping spacetime. If gravity is not a fundamental force but an emergent one, then the story of the universe becomes stranger than we ever imagined. The usual picture of physics rests on 4 pillars: the strong force, the weak force, electromagnetism, and gravity. Each of the first 3 has been successfully woven into the quantum framework, with force carriers and equations that describe them to astonishing precision. Gravity has always stood apart, proud and aloof, the most obvious, yet the least understood. But if it is emergent, then perhaps it does not belong on that list at all. Perhaps gravity is more like sound or pressure, patterns that are undeniably real, but not elemental. This shift in perspective changes the way we think about the cosmos. Take the problem of dark matter. For nearly a century, astronomers have been puzzled by the way galaxies spin. According to Newton and Einstein, stars near the edges of galaxies should orbit more slowly than those near the center, just as planets farther from the sun move more slowly. But observations show that stars in galaxies move too quickly, as if some unseen mass were tugging them. The dominant explanation has been dark matter, an invisible substance thought to outweigh ordinary matter by 5 to 1. Yet dark matter has never been detected in laboratories, and its nature remains mysterious. Verlinder's emergent gravity offered a bold alternative. In his framework, the apparent need for dark matter vanishes. The extra pull comes not from hidden particles, but from the way entropy and information are distributed across space-time. It is as if the geometry of the cosmos has hidden bookkeeping rules. And when stars move in galaxies, those rules add extra curvature. Some galactic rotation curves fit this model remarkably well, giving hope to those who doubt the existence of dark matter. But other observations, such as the distribution of matter in galaxy clusters and the imprint of dark matter on the cosmic microwave background, fit the traditional dark matter picture more closely. The debate remains unresolved, a tug-of-war between two visions of reality. If emergent gravity is correct, then manipulation takes on a new meaning. We would not seek to build machines that generate gravitons or warp fields. Instead, we would look for ways to manipulate information, entropy, and the microscopic degrees of freedom that underlie space-time. Imagine the universe as a great hologram, where the three-dimensional reality we see emerges from information encoded on a deeper surface. In such a universe, to change gravity would mean to alter the holographic code. It is a breathtaking thought, as if the world were a program and gravity one of its emergent algorithms. To control it would be to hack the code of reality. The philosophical consequences are immense. If gravity is emergent, then our everyday experience of weight is not a direct interaction, but a macroscopic illusion, as real to us as heat or pressure, but not fundamental. This challenges not only physics but also our sense of what is real. It forces us to admit that the universe may be more like a system of information than a system of objects, that what we take for solid ground is the projection of deeper laws. The dream of manipulating gravity becomes at once more distant and more profound. We may never build a gravity switch, but we may one day learn to sculpt the information field that makes gravity possible. Skepticism, of course, is vital. Emergent gravity is a young idea, and like many young ideas in physics, it may ultimately fail. Observations could rule it out. Experiments might confirm dark matter particles, ending the need for emergent explanations. But even if emergent gravity proves wrong in its details, it has already succeeded in broadening the conversation. It has shown that gravity is not beyond questioning, that even the oldest and most familiar of forces can be reimagined. Science advances not only through confirmations but also through challenges, and emergent gravity is a challenge of the highest order. At its core, the notion of gravity, as emergent, asks us to accept that the universe is not what it seems. It is not a stage of empty space, with objects moving upon it. It is a tapestry woven from information, entropy, and microscopic rules we have only begun to glimpse. To manipulate gravity in such a universe is to imagine manipulating that tapestry itself, not by pulling on threads we can see, but by altering the hidden pattern beneath. This line of thought prepares us for even more radical speculations. If gravity is emergent, then perhaps space-time itself is emergent. If space-time is not fundamental, then wormholes, warp drives, and exotic geometries may be less like engineering projects and more like computational rearrangements of information. What we call impossible today may in the future be reframed, not as feats of brute force, but as feats of subtle coding. The dream of controlling gravity may never look like science fiction imagined. It may instead look like rewriting the laws that produce the illusion of gravity in the first place. The next stage of our journey is to confront those exotic possibilities directly. If gravity is geometry, if space-time itself can be shaped, then general relativity offers solutions that sound fantastical. Warp drives that shrink distances, wormholes that link distant places, and exotic matter that bends the rules. These ideas are speculative, often beyond reach, yet they are written in the equations themselves. To move from emergent gravity to engineered spacetime is to step into the realm of warp bubbles and wormholes, where mathematics allows what engineering does not yet. The suggestion that gravity may be emergent unsettles us because it blurs the boundary between what we think of as real and what might be illusion. We feel the pull of Earth every moment, anchoring our bodies, shaping our lives. If that pull is not a force but an effect of information and entropy, then even the most familiar sensation in the universe is less direct than we believe. This is not to say gravity is unreal. Heat is not fundamental either, yet no one doubts its reality when flames burn. Emergent phenomena are as real as their foundations, but their reality lies in collective behavior, not in elemental particles. Consider temperature. It does not exist in a single molecule, which can move faster or slower, but does not have a temperature on its own. Only when countless molecules dance together, colliding and sharing energy, does temperature emerge. It is a property of the crowd, not the individual. If gravity is like temperature, then no single particle carries it. Instead, it arises from the collective behavior of something deeper, whether strings, loops, or bits of quantum information. In this way, emergent gravity reframes the search. Instead of hunting for gravitons, we should be hunting for the hidden microstructure of space-time. This vision is reinforced by hints from black hole physics. When Stephen Hawking showed that black holes emit radiation, he tied gravity to thermodynamics. Black holes have entropy proportional to the area of their event horizons, not their volume. They have temperatures, they evaporate, they obey laws that mirror those of ordinary thermodynamics. These discoveries suggest a deep link between gravity and information. The holographic principle, born from these insights, proposes that everything inside a region of spacetime can be described by information encoded on its boundary. If true, spacetime and gravity themselves may be holograms, projections of a deeper information structure. If gravity is a holographic illusion, then the path to manipulation becomes stranger still. To bend gravity would be to alter the code written on the boundary. It would mean reaching into the information that defines reality and rewriting it. Such an idea sounds more like myth than physics, yet it emerges naturally from the mathematics. Already, physicists use holographic dualities like ADS, CFT to study black holes and quantum fields, treating them as two sides of the same coin. These tools show that information and geometry are entwined, that the shape of spacetime may be nothing more than the shape of information. This does not mean we are anywhere near manipulating gravity by altering code. The analogy of temperature helps again. For centuries, humans lived with heat without knowing its molecular origin. Only when physics revealed the microscopic basis did we learn to harness it fully, to build engines and refrigerators. If gravity is emergent, then we stand now where humanity once stood with heat, aware of its effects, but ignorant of its true source. To harness it will require discovering the deeper rules, the molecular equivalent for spacetime. The implications for cosmology are equally staggering. If gravity is emergent, then the dark matter mystery may not require invisible particles at all. Instead, the anomalies in galaxy rotations may be natural consequences of the emergent framework. Dark energy, the strange acceleration of the universe's expansion, might also find explanation in the bookkeeping of information. In this sense, emergent gravity could unify mysteries that have long resisted solution, yet evidence remains ambiguous. Observations of galaxy clusters, gravitational lensing, and the cosmic microwave background all point strongly toward dark matter. Emergent gravity explains some patterns elegantly, but struggles with others. The debate is far from over. Still, even in uncertainty, emergent gravity forces us to confront possibility. What we call fundamental may be no more than appearance. What we call impossible may simply be hidden. If gravity is emergent, then controlling it may mean uncovering and mastering the rules that underlie spacetime itself. Whether through entropy, holography, or information theory, The frontier lies in seeing through the illusion to the code beneath. As we close this chapter, one thing becomes clear. Emergent gravity does not make the dream of control easier. In some ways, it makes it harder, for it removes the simplicity of a particle to catch or a field to manipulate. Yet it also expands the dream, suggesting that if gravity is born from information, then control of gravity may mean control of reality's most basic language. That is a dream worthy of science fiction and science alike, for it hints that to master gravity is not only to master motion, but to master existence itself. The journey now turns to the speculative edge of general relativity, where equations allow strange solutions that sound like fantasy. Warp drives, wormholes, and exotic matter all lurk in the mathematics. Possibilities that tantalize but demand resources we have never seen. If emergent gravity shows us that gravity may not be fundamental, then these exotic geometries show us how space-time itself might be bent. To explore them is to ask whether manipulation lies not in particles or information, but in engineering the very architecture of the cosmos. The equations of general relativity are precise, elegant, and unforgiving. They describe how mass and energy curve space-time, and how that curvature guides the motion of objects. Yet within those equations lie solutions that seem almost fantastical, solutions that stretch the imagination as far as the universe itself. Among these are warp drives, wormholes, and the tantalizing possibility of exotic matter. For decades, these ideas have occupied the uneasy ground between hard science and speculation, a place where mathematics whispers that something is possible, even as reality reminds us it may never be practical. The most famous of these possibilities is the Alcubierre warp drive, proposed in 1994 by Miguel Alcubierre, a Mexican theoretical physicist. Inspired by the starships of fiction, Alcubierre wondered whether Einstein's equations could permit faster than light travel without breaking the laws of physics. Surprisingly, they could. His solution described a bubble of spacetime that contracts in front and expands behind, carrying a spacecraft forward faster than light relative to outside observers. Inside the bubble, the ship itself never moves faster than light, so no rules of relativity are broken. It is spacetime itself that moves, and within its flow, the ship rides as if on a cosmic wave. At first glance, this sounds like fantasy, but the mathematics was sound. General relativity allows spacetime to expand faster than light, as the universe itself did during cosmic inflation. Alcubierre's warp bubble was another example of this principle. The catch is that creating such a bubble requires exotic matter, a form of energy with negative density. Ordinary matter has positive energy density, curving spacetime inward like a well. Negative energy would curve it outward, creating repulsive effects. In Alcubierre's model, enormous amounts of negative energy would be required, perhaps more than the mass of the observable universe. Negative energy is not entirely fiction. In quantum physics, the Casimir effect demonstrates that vacuum fluctuations can produce tiny amounts of negative energy between closely spaced plates. These effects have been measured in laboratories, showing that negative energy is real, but the amounts are infinitesimal. To build a warp bubble would require scaling this effect up to astronomical proportions, something no known technology can approach. Critics argue that the energy requirements make the warp drive permanently impractical. Optimists counter that refinements to the model might reduce the energy needs, perhaps even to scales within reach of future civilizations. Wormholes are another speculative offspring of Einstein's equations. A wormhole is a tunnel through spacetime, connecting two distant points. In principle, a traveler entering one mouth could emerge instantly at the other, no matter how far apart they are in ordinary space. The equations of general relativity permit such structures, known as Einstein-Rosen bridges. Yet the original solutions were unstable, collapsing too quickly for anything to pass through. Later work suggested that exotic matter with negative energy density could stabilize a wormhole, holding it open like braces hold open a tunnel. Like warp drives, wormholes live on the edge of plausibility. They are mathematically consistent, yet physically unproven. No evidence of a natural wormhole has ever been found, and the engineering required to create one exceeds anything humanity can imagine. Still, the possibility has inspired serious scientific study. Wormholes offer a potential explanation for certain puzzles in physics, such as how information escapes from black holes, or whether the universe is fundamentally connected in ways we cannot see. They also fire the imagination, suggesting shortcuts through the cosmos, doors to distant galaxies, or even pathways through time itself. Exotic matter is the common thread. Both warp bubbles and traversable wormholes require it. But exotic matter remains elusive. Quantum effects can produce small amounts, but whether large amounts can exist stably is unknown. Some theorists argue that the laws of physics forbid it, while others note that the laws of physics have surprised us before. Without exotic matter, these solutions remain dreams. With it, they might become realities. What makes these ideas compelling is not only their mathematical possibility, but also their narrative power. They remind us that the universe is stranger than common sense suggests. Relativity is not a cage, but a canvas, capable of shapes and patterns that seem like fiction until equations reveal them. Even if warp drives and wormholes never leave the page, their presence in the mathematics shows us that the laws of physics are not as simple as falling apples and circling planets. They contain surprises, some of which may lie forever beyond reach, but all of which expand our sense of what might be. The question for us is not whether these solutions exist on paper. They do. The question is whether the universe permits them in practice. Can negative energy exist in large amounts? Can wormholes remain stable long enough to traverse? Can a warp bubble be created without tearing itself apart? These questions are unanswered, but they set the stage for what comes next. For to understand whether gravity can be manipulated, we must look not only at the mathematics, but at the experiments. And the experiments tell a sobering story. The mathematics of warp drives and wormholes seduces the imagination, but the sobering reality lies in the gap between equations and engineering. Alcubierre's warp bubble, while elegant, demands more than just exotic matter in unthinkable quantities. It also requires control of space-time itself, with precision, finer than anything we can dream of today. To picture the difficulty, imagine trying to sculpt the ocean into a perfect wave that carries a ship forward, not by pushing it through the water, but by moving the water itself in just the right way. Now multiply that complexity to cosmic scales, and you begin to see the challenge of bending space-time on command. The same is true of wormholes. The idea that tunnels could connect distant regions of space-time is more than a fantasy. It is permitted by Einstein's field equations. Yet those same equations warn that such structures are unstable. Left to themselves, wormholes pinch off in an instant, closing before anything can pass through. To keep one open requires exotic matter with negative pressure to prop it up against collapse. This is not a minor requirement. It is as if you built a tunnel through a mountain that immediately crumbled, unless reinforced by a material that may not even exist. Physicists have explored the Casimir effect as a possible source of negative energy. When two metal plates are placed extremely close together in a vacuum, quantum fluctuations of empty space are restricted between them. This creates a measurable pressure that pushes the plates together, an effect that can be interpreted as a tiny region of negative energy. It is real, it has been observed, but it is minuscule. The energy available is so small it could not stabilize even a microscopic wormhole, let alone one large enough for a spacecraft. Still, its existence keeps the door open. It proves that negative energy is not pure fiction, though harnessing it remains a distant dream. Another complication arises from the paradoxes these solutions introduce. Wormholes, for instance, are often associated with time travel. If one mouth of a wormhole is accelerated or placed in a strong gravitational field, time may pass differently for each end. A traveler who enters the wormhole might emerge not only at another place but also at another time. This leads to paradoxes that strain causality itself. The equations do not forbid them, but nature may. Many physicists suspect that some principle, not yet fully understood, prevents such paradoxes by forbidding traversable wormholes altogether. The warp drive faces its own paradoxes. If faster-than-light travel were possible, it could allow information to move backward in time from some perspectives, creating causality loops. The equations of general relativity permit such scenarios, but whether the universe does is another matter. Some scientists suspect that quantum effects would destroy warp bubbles before they could form, a kind of cosmic censorship that protects causality. Others argue that the energy requirements, even if reduced, remain so vast that practical construction is effectively impossible. Despite these obstacles, the allure of these concepts persists. They serve as thought experiments, ways to test the boundaries of physics. By asking whether warp drives or wormholes are possible, scientists probe the limits of relativity, quantum theory, and the nature of energy. The answers refine our understanding, even if the final verdict is impossibility. Sometimes, impossibility itself is a discovery, a guidepost marking the edge of the possible. And yet, there is room for humility. Many ideas once deemed impossible have later become real, heavier than air flight, nuclear energy, and quantum entanglement. All seemed absurd in their time. The mathematics of relativity contains surprises that we may not yet fully grasp. To dismiss warp drives and wormholes as forever impossible may be as premature as dismissing flight was to those who lived before the Wright brothers. The universe is stranger than our common sense, and its laws contain possibilities that still astonish us. But science demands more than astonishment. It demands evidence. And when we leave the realm of theory and enter the laboratory, the story becomes far more grounded. Attempts to build or detect even the faintest forms of gravity manipulation have met with mixed results, from claims of anti-gravity in superconductors to the failures of replication that followed. To understand whether humans can truly engineer gravity, we must turn next to the experiments, where ambition collides with reality, and where extraordinary claims have often failed to survive the test of evidence. The very existence of warp drives and wormholes in Einstein's equations reveals something profound about gravity. It is not a simple force pulling objects together. It is the architecture of the universe itself, and that architecture can, in principle, take on bizarre shapes. Curved spacetime allows shortcuts, bubbles, bridges, and folds, possibilities that break free of the straight lines and rigid limits we usually imagine. This is why these solutions captivate both physicists and storytellers. They remind us that the universe is not limited to the familiar. It contains doors we can glimpse in mathematics, even if we cannot yet open them in reality. But even within the realm of equations, these solutions are precarious. The Alcubierre warp drive, for example, not only requires negative energy, but also suffers from horizons at the edge of the bubble, where information from outside cannot reach the inside. This raises questions about navigation. A ship inside might not be able to steer its bubble, because signals from the outside would be cut off. Wormholes, too, face issues of stability and feedback. Quantum fluctuations could race through them, destabilizing the tunnel and causing collapse. These difficulties may not be accidental. They may be nature's way of closing loopholes that would otherwise allow violations of causality. Exotic matter remains the linchpin. Without it, warp bubbles deflate and wormholes collapse. With it, space-time could be reshaped in ways that defy ordinary understanding. The trouble is that exotic matter is not something we can mine, refine, or manufacture in bulk. It is a quantum phenomenon, appearing only in fragile, fleeting contexts like the Casimir effect. Even if it could be produced, storing and handling it would raise challenges unlike anything we know. Ordinary matter attracts, exotic matter repels. A single misstep might release energies that cannot be contained. Still, The mere possibility of exotic matter excites scientists because it pushes the boundaries of what physics considers possible. It is a reminder that the vacuum is not empty but teeming with fluctuations, that negative energy is not forbidden but already present in nature's quantum play. Even if warp drives and wormholes remain dreams, the study of exotic matter may reveal other practical uses, from precision measurements to advances in quantum technologies. In this sense, speculation can fertilize discovery, leading us toward advances not imagined at the outset. For humanity, the allure of these ideas is more than scientific. They represent the ultimate escape from gravity's tyranny. A warp bubble promises freedom from the speed limit of light. A wormhole promises shortcuts across the stars. Exotic matter promises the tools to bend space-time itself. Each idea reflects our desire to transcend the obstacles that hold us to Earth. They are metaphors as much as mechanisms, symbols of our refusal to accept limits. Whether they are ever realized in engineering does not diminish their role in inspiring imagination and testing the boundaries of knowledge. And yet, science is a discipline of skepticism. It is not enough to find a solution in an equation. Nature is the final judge. Without evidence, warp drives and wormholes remain elegant dreams. To move forward, we must examine what happens when experiments reach for gravity in the laboratory, and history shows that many such attempts, from anti-gravity claims to superconducting anomalies, have faltered under scrutiny. Extraordinary claims demand extraordinary evidence, and gravity has so far resisted every shortcut we try. As our journey continues, we turn now from the heights of speculation to the harsher ground of experiment. The next chapter explores the failed attempts and fringe claims that have dotted the history of gravity research, from Podkletnov's supposed gravity shielding to the countless replication failures that followed. These stories remind us why skepticism is essential and why gravity remains the most stubborn of all the forces to tame. The human longing to break free of gravity has never been satisfied with theory alone. Equations, however elegant, leave us yearning for demonstration, for evidence that the impossible can be made real. Throughout history, whenever bold new ideas emerge, there are those who attempt to bring them down to earth, to coax them into the laboratory, to show the world that the dream is already within our grasp. But gravity, stubborn as ever, has a way of punishing premature ambition. The story of failed experiments and fringe claims is as much a part of the history of science as the triumphs, a reminder that discovery is often built upon disappointment, and that extraordinary claims demand extraordinary evidence. One of the most famous and controversial episodes in this story unfolded in the 1990s, when a Russian physicist named Eugene Podkletnov claimed to have discovered a form of gravity shielding, working with superconductors, materials that conduct electricity without resistance at low temperatures. Podkletnov reported that objects placed above a spinning superconducting disk lost a small fraction of their weight. The effect was slight, only about 1 or 2%, but if true, it was revolutionary. Anti-gravity, long the realm of science fiction, seemed to have stepped into the laboratory. Newspapers ran sensational headlines, governments took notice, and laboratories around the world scrambled to replicate the result. But replication never came. Careful attempts by multiple independent groups failed to reproduce Podkletnov's observations. The supposed weight loss could not be confirmed, and many scientists concluded that the effect was an experimental error. Podkletnov himself withdrew from the spotlight, though he maintained that his results were genuine. To this day, his claims remain a cautionary tale. They demonstrate the allure of extraordinary results and the importance of skepticism. Gravity is universal, consistent, and precise. If it could be shielded by spinning superconductors, it would upend centuries of physics. Such a claim requires evidence so clear, so undeniable, that doubt is impossible. Podkletnov's work did not meet that standard, and history has largely placed it in the category of fringe science. The allure of superconductors did not end there. Other researchers have speculated that quantum effects in superconducting materials might produce anomalous gravitational behavior. Some experiments reported faint signals, strange anomalies that hinted at new physics, but none have stood the test of replication. In the end, the lesson was the same. Anomalies are not discoveries until they can be repeated reliably, until they survive the harsh light of independent scrutiny. Gravity has resisted every such attempt, remaining immune to shortcuts. Podkletnov's story is far from unique. Throughout the 20th century and into the 21st, countless inventors and fringe researchers have claimed to build anti-gravity machines. Some were driven by genuine curiosity, others by the lure of fame or fortune. Many of these devices relied on spinning objects, rotating magnets, or high-voltage discharges, all designed to mimic the cosmic dance of celestial bodies. They promised hovering platforms, fuel-free propulsion, or shields against weight. Yet when tested under controlled conditions, they all failed. The pattern is striking. The closer the scrutiny, the weaker the effect, until nothing remained but ordinary physics. One reason such claims persist is that gravity is both familiar and mysterious. We live with it constantly, but we do not fully understand it. This makes it an inviting target for speculation. Unlike electricity or magnetism, which can be controlled with wires and circuits, gravity offers no easy handle. The dreamers imagine that perhaps some overlooked principle could unlock the door, some simple trick waiting to be discovered in a basement workshop or improvised laboratory. History encourages this hope. For electricity, radio, and even nuclear power began as mysteries that yielded to curiosity. But gravity has proven more resistant, perhaps because it is not a force we can insulate or block, but the very curvature of space-time itself. Skepticism, however, is not cynicism. Science does not dismiss claims because they are bold. It tests them. If evidence holds, boldness becomes discovery. If it crumbles, boldness becomes a lesson. The failed claims of anti-gravity do not weaken science. They strengthen it, showing that the methods of verification work, that truth is not decided by press releases or headlines, but by results that anyone, anywhere, can replicate. The failures remind us that reality is not swayed by desire. Gravity bends to no one's ambition. Even in mainstream science, experiments at the edge of detection have faced similar challenges. When researchers measure tiny gravitational effects between small objects, noise and error creep in. Vibrations, temperature changes, and electromagnetic interference can all mimic weak signals. Separating real gravitational effects from these imposters is immensely difficult. This is why extraordinary claims must meet extraordinary standards. The smaller the effect, the greater the burden of proof. Without rigorous confirmation, anomalies remain curiosities, not breakthroughs. The persistence of fringe claims also tells us something about human nature. We yearn for shortcuts, for miracles that deliver progress, without the slow grind of research. Anti-gravity machines promise instant revolutions, skipping the decades of patient work required to understand the problem. They feed the imagination and inspire speculation, but they also distract from the real progress being made. The detection of gravitational waves, the measurement of frame dragging, the precision of satellite navigation, all these are genuine achievements, born of rigorous science. They may lack the glamour of flying discs or gravity shields, but they are steps toward understanding that will endure long after the fringe claims are forgotten. And yet, we should not dismiss the dreamers entirely. For every failed experiment, there is also the possibility that one day, someone will stumble upon something real. Science thrives on curiosity, even misguided curiosity. The boundary between fringe and frontier is not always obvious. Ideas once mocked as impossible, such as quantum entanglement or black holes, are now pillars of physics. The difference is not in the boldness of the idea, but in the rigor of the evidence. Until that rigor is met, The extraordinary claims of antigravity remain parables, warnings etched into the history of physics. The lesson of this chapter is clear. Manipulating gravity is not easy. It is not something that can be achieved with spinning disks or high-voltage gadgets. It is a challenge at the very limits of our understanding, one that will not yield to shortcuts or errors. But the failures themselves have value. They teach us humility, they sharpen our skepticism, and they remind us of the importance of evidence. They also reveal the hunger that drives us, the desire to defy gravity and step beyond Earth's hold. That hunger is real, even if the shortcuts are not. From here, our journey moves to the laboratory once more, but this time, not through failures and illusions. The next chapter explores the tiny triumphs that science has achieved in manipulating gravity, subtle but real. From centrifuges that simulate weight to measurements of negative energy in quantum fields, these successes are modest compared to the dreams of antigravity, but they are grounded, tested, and enduring. They show that progress is possible, even if it comes in small steps rather than leaps. They are the seeds of hope in a field where disappointment has been plentiful, the faint but genuine light that guides us toward the future. If the story of gravity manipulation is filled with failures and unproven claims, it is also illuminated by small but undeniable successes. These are not the spectacular victories of science fiction, no anti-gravity engines or hovering platforms, but they are real achievements, measured and confirmed. They represent humanity's first genuine steps toward understanding how to work with gravity, rather than against it. In their modesty lies their importance, for they show that even if gravity cannot be switched off, it can be shaped, simulated, and nudged in ways that matter. The most straightforward triumph is the creation of simulated gravity through acceleration. Albert Einstein's equivalence principle tells us that acceleration and gravity are indistinguishable. A person in a sealed box cannot tell whether the pressure they feel against the floor comes from Earth's pull or from the box being accelerated through space. This principle has been tested and confirmed countless times, and it is the basis for artificial gravity in rotating space stations. A centrifuge, spinning with the right speed, presses objects against its walls in a way that mimics weight. Astronauts on long missions have already used short-arm centrifuges to counteract bone and muscle loss, and designers of future habitats envision massive rotating structures where centrifugal force supplies what Earth once did. It is not true gravity, for the effect varies with distance from the axis, but it is real enough to sustain life. Another triumph lies in measuring the smallest twists and ripples of space-time. The detection of frame dragging by the Gravity Probe B mission is a milestone in gravity engineering. Frame dragging is the effect predicted by general relativity in which a rotating mass drags space-time around with it. Earth does this subtly, twisting space-time as it spins. In 2011, after years of data collection, Gravity Probe B confirmed this effect with precision, measuring how tiny gyroscopes shifted their orientation as Earth's rotation pulled on space-time itself. The shift was minuscule, just a fraction of a degree over a year, but it was real, and it was measured. This was gravity manipulation observed, not engineered, but it proves that mass and motion shape the fabric we live in. Even more profound are the triumphs of gravitational wave detection. In 2015, the LIGO observatories recorded the first direct signal of gravitational waves, ripples in space-time produced by colliding black holes more than 1 billion light-years away. The stretching and squeezing of space-time was smaller than the width of a proton, yet it was measured with confidence. This is not manipulation in the sense of control, but it is the use of human ingenuity to listen to gravity's faintest whispers. To detect such waves is to participate in the geometry of the universe, to capture the evidence that space-time itself moves and flexes. It is a triumph of measurement, one that opens the door to future generations who might learn not only to detect, but to create such waves. At the quantum scale, there are hints that negative energy and exotic effects can be harnessed, at least in principle. The Casimir effect demonstrates that quantum fluctuations of the vacuum are not mere abstractions, but real forces. When two conducting plates are brought extremely close together, the quantum vacuum between them changes, producing a measurable attraction that can be interpreted as negative energy density. While the effect is tiny and difficult to exploit, it proves that the vacuum itself can be engineered at small scales. This is the kind of subtle control that future technologies may expand upon. If negative energy is ever produced in bulk, the foundations of warp drives and wormholes could move from speculation to engineering. For now, it remains a faint triumph, proof that exotic physics is not wholly out of reach. Practical applications of these small victories are already visible. Centrifuges and rotating stations may allow humans to survive long voyages through space, turning the equivalence principle into a tool for exploration. Gravitational wave observatories give us a new way to study the universe, opening a window that no other force can provide. Precision measurements of frame dragging and subtle gravitational anomalies sharpen our understanding of Earth's structure and the behavior of space-time. These are not breakthroughs that will change civilization overnight, but they are the building blocks of a deeper mastery. They remind us that even giants begin as seeds. What is most striking is how these triumphs reveal the nature of progress. Gravity has not yielded to spectacular machines or miraculous shortcuts. It has yielded to patience, to careful measurement, to incremental steps. Each success builds on what came before, each experiment pushing the limits of precision a little further. This is how science moves forward, not in leaps, but in steady marches, until what once seemed impossible becomes routine. And yet, even in their modesty, these triumphs hint at something greater. The ability to simulate gravity in space, to measure the curvature of space-time, to detect the ripples of black hole collisions, all of these point to a future where control may grow. If we can measure frame dragging, might we one day amplify it? If we can detect gravitational waves, might we one day generate them intentionally? If we can alter the vacuum in the Casimir effect, might we one day sculpt space-time itself? The triumphs are small, but they are real, and they whisper of possibilities yet to come. From these achievements, our imagination leaps ahead. What would it mean if humans could control gravity not just indirectly but directly, bending it to our will? The applications would be staggering. From propulsion that frees us from rockets, to colonies that float in orbit, to weapons that shape battlefields with invisible force. The consequences would be ethical as much as scientific, reshaping civilization itself. The next chapter will explore this vision, asking not whether we can control gravity today, but what the world would look like if one day we could. To imagine what humanity might achieve if it ever learned to control gravity is to step into a vision so sweeping it borders on myth. Gravity is not just one force among many. It is the architect of the cosmos, the shaper of galaxies, the anchor of worlds. To control it would be to take hold of the scaffold on which reality itself is built. It is a dream that has haunted mythologies and inspired stories of flying chariots and anti-gravity machines. But if realized in practice, its impact would surpass anything imagined in legend. It would redefine civilization from its foundations to its frontiers. The most obvious application would be propulsion. Today, every rocket that leaves Earth must claw its way up against gravity's grip, burning colossal amounts of fuel to escape. Controlling gravity would make this struggle obsolete. A ship could simply switch off its weight, floating free of Earth's pull. Interplanetary travel would become trivial. Colonies on the Moon, Mars, and beyond would flourish as easily as cities on Earth, supplied by ships that rise and land without effort. Entire economies would shift, for transport costs across the void would drop to almost nothing. Humanity's expansion into space, now constrained by resources and risk, would accelerate beyond imagination. But propulsion is only the beginning. Energy itself could be revolutionized. Gravity wells are vast reservoirs of potential energy. If we could manipulate them, we might tap into new sources of power, drawing on the curvature of space-time, the way we now draw on chemical or nuclear reactions. Machines could be built that convert controlled changes in gravity into electricity, powering civilizations with the very geometry of the cosmos. On planetary scales, we could imagine rebalancing tides, controlling planetary spins, or even shifting orbits to maintain habitability. Civilizations that control gravity would no longer be at the mercy of stars and planets. They would shape their own environments with cosmic tools. The colonization of space would take on new dimensions. Artificial gravity could be engineered without the need for spinning stations. Habitats could have adjustable weight, tuned for comfort or efficiency. Worlds without sufficient gravity, like asteroids or small moons, could be endowed with artificial pull, making them suitable for permanent settlement. Conversely, crushing worlds with high gravity could be tamed, allowing humans to walk on surfaces that would otherwise be uninhabitable. With such power, every corner of the solar system could become a home, every rock and fragment a potential foundation for life. The consequences for warfare are equally staggering and equally terrifying. Gravity control could become the ultimate weapon. A localized increase in pull could crush armies or buildings in an instant. A sudden reduction could fling objects and people into the sky. Beams or waves of manipulated spacetime could disable satellites, collapse bunkers, or even destabilize planets. The weaponization of gravity would make nuclear arsenals seem primitive by comparison. Wars would no longer be fought with explosions, but with the reshaping of the environment itself. The ethical and political challenges of such technology would be immense, forcing humanity to confront questions of restraint and survival on a new scale. Even more profound are the philosophical consequences. If we controlled gravity, we would control the curvature of space-time, and thus time itself. In relativity, gravity and time are inseparable. Stronger gravity slows the flow of time, weaker gravity speeds it. By shaping gravitational fields, civilizations might one day shape the very experience of time, accelerating it for computation, slowing it for preservation, even bending it for communication across vast distances. The myths of time machines and eternal youth might find echoes in the engineering of space-time, not through fantasy, but through physics. Civilization itself would be reshaped. Cities would no longer be bound by geography. Floating platforms could drift above oceans, mountains, or even planets without surfaces. Structures could rise kilometers high without collapsing, supported by engineered gravity. Transportation would become seamless, with vehicles that hover without effort, powered not by thrust, but by space-time itself. The division between ground and sky, Earth and orbit, planet and space, would dissolve. Humanity would become a species of space-time, living not just on worlds, but within engineered regions of curvature, tailored to its needs. And yet, such power comes with peril. The history of technology warns us that every tool can be weaponized. Every discovery carries unintended consequences. The control of gravity would be no different. Its misuse could devastate civilizations, unmake planets, or destabilize stars. The political structures required to manage such power would have to evolve beyond anything we have today. It would demand unprecedented cooperation, restraint, and wisdom. Without them, the very power that frees us from gravity's chains could become the instrument of our extinction. Still, the vision is irresistible. To control gravity would be to step into the role once reserved for gods, to command not just matter and energy, but the geometry of existence. It would fulfill humanity's oldest dream of freedom, lifting us from Earth, not only physically but existentially, into a future where limits themselves are negotiable. Whether such control is possible is uncertain, perhaps even unlikely. But to imagine it is to glimpse the scale of what gravity means. It is not just a force to overcome, it is the framework of reality, and to hold it in our hands would be to hold the future itself. But reality today remains far humbler. We cannot bend space-time at will. We cannot shield gravity or create it in the laboratory. Our triumphs are modest, our failures numerous, our ambitions still checked by the stubborn consistency of nature. And so, as this journey approaches its end, we must ask, what is the verdict on gravity manipulation? What have we truly achieved? What remains possible? And what belongs forever to fantasy? The next and final chapter seeks to answer this, to sift through the myths, the mathematics, the experiments, and the dreams, and to deliver a judgment on whether humanity will ever tame the force that holds the stars together. From the first myths of flying chariots to the modern dreams of warp drives, humanity's longing to control gravity has been a constant thread. It is the one force that defines our lives most intimately, binding us to Earth, guiding the stars, and shaping the cosmos. To master it would be to master the stage on which existence unfolds. But as we draw together the strands of history, theory, experiment, and speculation, what verdict can we deliver? Is gravity manipulation truly possible? Or is it a dream, forever, out of reach? The evidence so far is sobering. Gravity, unlike the other forces, has resisted every attempt at direct control. Electromagnetism yields to wires and fields. The nuclear forces yield to accelerators and reactors. But gravity remains aloof. It cannot be shielded, reflected, or amplified by any known means. Our greatest achievements with it have been indirect. The orbiting of spacecraft, the detection of waves from colliding black holes, the measurement of frame dragging. These are triumphs of understanding, not of mastery. They prove that we can listen to gravity, measure it, and use its predictable consistency, but not that we can bend it to our will. The theoretical frameworks offer both hope and caution. General relativity shows us that space-time can curve in exotic ways, permitting solutions like warp bubbles and wormholes. These are not fantasy, they are written into the mathematics. Yet the mathematics also demands exotic matter, negative energy, and quantities of resources beyond imagination. Without these, the solutions collapse, and with them, the dreams of faster-than-light travel or shortcuts through space-time. The equations whisper possibility, but they also warn of costs so great that they may as well be prohibitions. Quantum theory deepens the mystery. If gravity is carried by gravitons, then in principle it could be manipulated like other forces. But gravitons, if they exist, are almost impossible to detect, let alone control. Their interactions are so weak that even an Earth-sized detector, running for the age of the universe, might not catch a single one. This makes them effectively inaccessible, keeping quantum gravity in the realm of speculation. And if gravity is not fundamental at all, but emergent from entropy and information, then there are no gravitons to catch. In that case, the very notion of controlling gravity becomes tangled with the even harder task of controlling the hidden information fabric of the universe itself. The experimental record reinforces the verdict of difficulty. Claims of anti-gravity, gravity shielding, or anomalous effects have all failed replication. Podkletnov's superconducting disks, spinning magnets, and countless fringe devices have collapsed under scrutiny. Gravity remains consistent, universal, immune to shortcuts. The only proven manipulations are indirect. Simulated gravity through acceleration, tiny measurements of negative energy in the Casimir effect, subtle detections of space-time curvature. These are genuine, but they are small. They do not bring us closer to turning gravity on or off, only to understanding its unyielding nature. And yet, to dismiss the dream entirely would be premature. Science has a way of turning impossibility into inevitability. Heavier than air flight, nuclear power, quantum computers, all were once unthinkable. The very equations of relativity suggest that exotic geometries are possible, even if they are impractical. Quantum theory proves that negative energy exists, even if only in small amounts. Emergent theories show that gravity may be a phenomenon born of information, hinting that its control might one day lie in fields we have not yet imagined. The verdict is not impossibility, but improbability, at least for now. If gravity is ever tamed, it will not come from shortcuts or fringe experiments. It will come from the slow grind of science, from decades of theory, measurement, and discovery. It may require entirely new physics, a revolution as profound as relativity or quantum mechanics. It may require understanding not just space-time, but the deeper fabric of information from which space-time arises. Such breakthroughs are not impossible. They are simply distant, demanding patience, rigor, and humility. So the verdict is this: gravity manipulation is mathematically possible, physically intriguing, but practically out of reach. With present knowledge and technology, the universe permits it in principle, but demands a price far beyond our current capacity to pay. It is not forbidden, but it is not ours. Not yet. And perhaps that is fitting. Gravity is the architect of the cosmos, the shaper of stars, and the keeper of worlds. To control it would be to step into the role of creator, to sculpt reality itself. Such power is not easily won, nor lightly held. For now, it remains a dream, one that inspires science fiction, fuels speculation, and drives the imagination of physicists who dare to ask. The dream will not fade, because it is bound to the deepest human desire: to rise, to move freely, to transcend limits. We close this journey not with certainty but with awe. Gravity remains untamed, but it is also the thread that connects us to the universe. It holds us to Earth, binds us to the sun, curves the paths of galaxies, and carries the ripples of colliding black holes across the void. To seek its mastery is to seek mastery of existence itself. And though the dream is distant, it is not dead. For as long as humans look up at the sky, we will wonder whether one day we might hold gravity in our hands. Gravity is the architect of the cosmos. To control it would be to control reality itself, a dream that physics whispers may be possible, but that the universe reminds us will demand a price far beyond our reach. For now,